Welcome to this video about simulating fluvial flooding with the FastFlood Rapid Flood Assessment Platform. Today we're going to look at simulating fluvial flood behavior without simulating the hydrology of the entire upstream catchment. And we're going to do this by using discharge boundary conditions at the inflow point of our model domain. Let's get started. I have the website right open, and what we can do is go ahead and move to the area that I'm interested in. And for now, that's an area that's part of the Koshi River system in Nepal. So let's have a look. So I have this, this non-urban area with very steep terrain, and maybe I want to model some flood processes here, but I don't want to model the entire hydrology. So what kind of solutions can we give? Well, the first thing we can do is go ahead and define our model area. So let's say I'm interested in this particular piece of the landscape. So I'm going to go ahead and download the SFTM data. Now, these global elevation datasets in this kind of steep terrain sometimes come with some issues in detecting the deepest parts of the valleys. So it can be beneficial to do hydrological correction. With using the default settings, we should be perfectly fine, and the processing is done. So this helps us a bit improve the quality later on. Now, what we can do now is say define a discharge boundary condition at the point where the river enters our model domain and specify the discharge value. Now, for now, I'm going to put that value at 800 cubic meters a second. And again, then, we're not interested in precipitation, so I'm going to put the precipitation value at 0 and press simulate. And there we go. Our flood model is done. Now, there's a couple things we can do to help improve the quality here. One of them is that in the settings, we can go to high accuracy, and this will give the solver in the background a little bit more time and a couple more iterations to actually extend the flood domain to where it should be. It doesn't make a lot of difference here, but it's a good practice to check. Additionally, what we can do is under the channel options, mention that we want to have monodirectional channels. And in this kind of setting, this tends to help a little bit. You can specify the minimum drainage area above which this should be used. For here, it's an option to use it everywhere since we are just modeling flow in this large river. So again, we go ahead. The changes are very minor, but it does help a little bit with the accuracy. Okay, so this is a way to do this. Now, sometimes you don't have discharge data available. Maybe there's no station measuring discharge and global datasets don't have any data available. Now, there is a built-in option for you there. So what we've done is we've taken the global flood forecasting model GLOFAS and reanalysis data that was published as part of that. And we've done a return period analysis for that. So if you're using the FastFlood Pro subscription, you can go ahead and click on the GLOFAS tool. And then you have access to return period data immediately right from the website. So you can see we have done that analysis globally, and we can select our river location right here and get the return period discharge values. We can also get the current forecast for the coming 2 weeks of discharge values in this station and use those then to set our boundary condition. So here a 50-year discharge return period discharge event would have a 404.996 cubic meters a second discharge value. So that's rounded off to 405. And we can go ahead and fill that in and do our simulation again. Now, this is an example of a non-urban area, but we can also have a look at an area that's a little bit different. So let's go to a more urban area. I'm going to go to a part of the Maas River system in Belgium, and I'm going to activate the different background layer so I can actually see where I am. There we go. So let's have a look at a more city-like environment. Again, I'm going to use the global elevation datasets, and here I'm going to use the Copernicus dataset that's available for those with FastFlood Pro usage. Once it's done processing that, Of course, it shows up the elevation data and it shows you the model domain. And again, what we can go ahead and do is define our discharge boundary condition. So again, I'm going to define here at the point where the river flows into our model domain, and I'm going to look at the return period values. I'm going to select the 20-year return period, so 1038 cubic meters a second. Now, in flat terrain, the routing that's part of the FastFlat model, sometimes because of elevation model errors, goes the wrong direction. You can help this a little bit by closing off the incoming side of your model domain by defining an artificial boundary there to make sure that the lowest outflow point towards which FastFlat routes the actual water is actually on the exit side of your model domain. Now again, we can go ahead and press simulate to actually model the behavior of the system with this discharge boundary condition. And there we go, we have our results. So what we see immediately is at the moment there's no flooding. The water is contained within the river. Now here the actual estimate of the river shape in the elevation model is quite good. The improved accuracy of the Copernicus global elevation model helps with this. This is not always the case. It's usually really good to check these kind of things. Right? Anyway, calibration and validation is critical when using these kinds of results. But especially for these kind of river systems, bathymetry data can be needed, and you sometimes have to provide your own elevation data sets to do good types of modeling. For now here, this is working reasonably well, and we should see that if we increase the discharge by quite an amount, we can actually see our flood behavior starting. And as you can see, when significantly increasing the discharge, we start to see the flood behavior that we would expect. Now in these kinds of urban environments, there's a lot more of detail that can be added based on human interventions that have been done, mitigation, pumping systems, stormwater drainage, sewer systems, and much more. Now there's some tools in FastFlat to help you with this. Besides discharge boundary conditions, you can also define pump and sewer type systems as well. You can implement levee systems and load them also from predefined shape files and other data. Thank you very much for watching this video. I hope it was helpful. If you're looking for more information, please visit fastflat.org. Thank you.